This split-screen graph shows two very different types of motion. On the left, a point traces a smooth, continuous path without any interruptions. On the right, the path has a sudden jump, forcing the tracing point to teleport across the gap. We can easily see the difference visually, but to do real analysis, we need to define that difference mathematically. Walter Rudin provides that exact standard in definition 4.5. The core of this definition relies on an epsilon-delta relationship to prove whether a function is truly continuous at a specific point. Let's look at how this plays out between two metric spaces, x and y. We pick a point P in x, which maps to a value in y. First, we set a strict error tolerance around our target value in y. We call this the epsilon bubble. To prove continuity, we have to find a specific starting boundary around P in x, the delta bubble. The rule is strict. Every single point inside that delta bubble must map entirely within our chosen epsilon bubble. If we can guarantee that precise landing zone for any epsilon we choose, the function is continuous at P. Theorem 4.6 connects this back to limit sequences. If P is a limit point, continuity simply requires the limit of the function to equal the exact value of the function at that point. There is also a brief exception. If P is an isolated point, meaning it has no immediate neighbors, the function is considered continuous there by default, because there is no way to violate the epsilon bubble rule. Local proximity in a starting space guarantees local predictability in the destination space. Small changes in input guarantee tightly bounded changes in output. Once we establish continuity for individual functions, we can combine them. Theorems 4.4 and 4.9 show that we can add, multiply, and divide complex continuous functions, and the resulting combinations remain continuous. Because standard limits perfectly respect basic algebra, adding or multiplying smooth behaviors together cannot spontaneously create a mathematical jump. As long as we avoid dividing by zero, the outputs stay predictable. We can also pass the output of one function directly into another. Theorem 4.7 governs this composition of continuous functions, written as h equals g of f. This creates a chain reaction across three metric spaces. A target tolerance in space C requires a specific boundary in space y. Because the first function is also continuous, that boundary in y immediately determines the necessary boundary back in space x. Complex continuous systems are reliably built by stacking simple continuous parts. We don't have to test an entire massive system from scratch if we know its individual components are continuous. Theorem 4.8 offers a completely abstract perspective on this concept. It states that a mapping is continuous if and only if the inverse image of every open set remains an open set. In the topological approach, projecting an open interval from the y-axis down to the x-axis of a smooth curve yields an open domain interval. But reverse mapping across a sudden jump forces the x-axis projection to include a closed boundary. This reveals hidden structural breaks. Take a moment to test this logic. Using the building blocks we just established, how would you prove that a standard polynomial equation is continuous everywhere? In higher mathematics, continuity is defined entirely by the structural preservation of open space. Example 4.11 provides the answer for polynomials. It breaks the entire equation down into isolated coordinate functions and constants. Constant functions and basic variables are continuous. Therefore, their products, like x squared, and their sums, like x squared plus x, must also be continuous. The property carries through every algebraic step until the polynomial is complete. The exact same logic applies to the absolute value, or norm function. By looking at the triangle inequality formula, we can see that simply setting our delta exactly equal to epsilon perfectly satisfies the continuity requirement across the entire space. We can distill continuity into four pillars. First, a sequence limit equals the function's exact value. Second, there are no sudden jumps. Third, continuous functions can be algebraically combined. And fourth, the inverse image of an open set is always open. Mastering these unbroken paths provides the foundation needed to study derivatives, integration, and deeper real analysis. Like, subscribe, and join us next time as we continue exploring the rigorous tools of higher mathematics.